Hey, welcome to Lecture Online. Now we're going to learn about some applications of the derivative. One of the applications is to find the maximum and minimum values on a function. And before we show you some examples how to do that, let's take a general approach, a general vision of what that really means. So here you have a segment of a function, f of x, which means there's a relationship between x values and y values. If we draw an axis on that, we can say that this here is the y-axis. Here this would be the x-axis, y-axis, like that. And notice that the function is delineated between -2 and 6. This would then be the domain from x equals -2 to x equals 6. When x is equal to -2, the function is 20. That means y is equal to 20. When x is equal to 6, y is equal to 14. And then there's some three very special values in between. When x is equal to 0, y is 0. X is equal to 2, y is 8. And x equal to 4, y is -6. Is of course it's not a real function, but it's just a good way to give you an example. Notice that the slope at these 3 points is equal to 0. Now what happens between all those points? Well, notice when we go from x equals -2 to x equals 0, the function is decreasing, meaning the value for y is getting smaller. That means here the slope is negative. So we can say that the function is decreasing, which means that the derivative f prime of x is negative, meaning it's less than 0. Now here, between x equals 0 to x equals 2, you can see that the function is increasing. As x is getting bigger, so y is getting bigger. That means the function here is increasing, and there the derivative f prime of x is therefore greater than 0. Now going from x equals 2 to x equals 4, you can see now that x is getting bigger, y is getting smaller. That means now the function is decreasing, and that means that f prime of x, the derivative, f prime of x, is therefore less than 0. And finally, from x equals 4 to x equals 6, here again the function is increasing. As x is getting bigger, y is getting bigger. That means the function is increasing. That means the slope is going to be positive, or f prime of x is going to be greater than 0. And I've kind of summed it up over here. If the function is increasing, the derivative is greater than 0. If the function is decreasing, the derivative is smaller than 0. But what happens at the point between where the function is decreasing and the function is increasing? That's that point right there. And of course, if the slope is negative here and the slope is positive there, then right in between the slope has to at some point be 0, and we call those critical points that I have circled right here. That's a very special point on a graph, and yes, derivatives help us find those critical points. I'll show you some examples of that. Now notice, of those 5 points, which of those 5 points is the highest, which has the largest y value? And of course that would be this right here. We call that the highest point on the interval, and we call that therefore the absolute maximum. So for the maximum values on our functions, we can have an absolute maximum value. That's the highest value the function can have on the interval from x equals -2 to x equals 6. What is the lowest value this function can have? It's right here, where y is equal to -6. That would be what we would call the maximum, or I'm sorry, the absolute minimum. I would say that the maximum minimum doesn't sound very good. It would be the absolute minimum point on the interval. Now what about these other 3 points right there? This is also a maximum, at least in this area. This is kind of like a local maximum point, and that's what we call it, a local maximum. In this small region of the graph, that is the highest point. Here, that is an absolute minimum, because that's the very lowest point of the graph. But what about this point right here? It also kind of dips down to a low point. It's not the lowest point. So in this vicinity here, that is the lowest point on the graph, so we call it a local minimum. And over here, again, in this particular region of the graph, that's the highest point. We call that the local maximum because it's not the greatest maximum. This is, of course, the absolute maximum, and this would then be called the local maximum. How do we find that? Well, we can find these points here by taking the derivative and then setting the derivative equal to 0, and then solve for the x value that then matches that point. And I'll show you some examples how to do that. So using the derivative, we can find these, what we call critical points, where the slope is equal to 0, by simply, again, finding the derivative of the function, setting it equal to 0, because we know when the slope is equal to 0, that means the derivative must equal to 0, because the slope is, of course, the derivative. And How can we know that these are maximum minimum values? Well, what we can do is we know that since these are the endpoints of the function, delineated between